Okay, so today we will work on the last section of the scattering and diffraction in chapter 10, that is diffraction. So diffraction you studied the diffraction in optical classes. If you send waves to the opening or the opaque matter, the waves, which is the wavelength lambda, and say that the opening is much greater than the wavelength, so these waves will diffract. And if you have a screen, you can obtain some diffraction pattern. Actually, diffraction and interference, it is hard to explain the difference between the diffraction and interference. So if you think about that, the Young double slit experiment, you can create an interference pattern. So some of the waves will be add up, some of the waves will be cancelled out, and you can obtain some interference pattern. But if you think about that, the opening with size A, and that is much larger than the wavelength, then you can think about that there are many sources there. This is the Huygens principle, and each source behaves as a source of some spherical wave, and the addition of this will be the diffraction. So double slit could be thought as a interference, and if you have an opening, and if the wavelength of the incoming waves are less than the opening, you can think about as that is diffraction. So who work until to the theory of the diffraction? So we have Huygens and we have Young double slit experiment and Fresnel diffraction theory. So today we will use the methods of the mathematical theory, let's say, or electromagnetic theory of the classical optics. So the classical optics different from the geometrical optics. So because their wave nature is much more important. So in our approach, we will have some region, let's say S1. In the S1 region, we have sources, and S2 region is the region at which we have a screen. And in S1 region screen, there are apertures, and the emitted light passes from the apertures or opaque matter, and we can observe them on the screen. So basically we have electromagnetic waves and boundaries. So the best approach is applied by the Kirchhoff, and he uses the Green's theorem. So Kirchhoff's method uses Green's theorem. So basically we have the volume and boundaries. It is natural to use the Green's theorem, but how we are going to use the Green's theorem in order to explain the diffraction. So basically that is explained, you can explain the diffraction by using the Huygens principle. That means that you have an opening and waves, some wavelength. Wavelength is less than the opening, and through the passage of the waves through the opening, you can think about many sources there, and each of them adding some little spherical waves, and the addition of that is the diffraction. So let us remember that the Green's theorem. So Green's theorem tells you that if you have a volume integral of, let's say, phi Laplacian of psi minus psi Laplacian of phi integrated through the volume is equal to a surface integral of phi del psi over del n minus psi del phi over del n integrated through the surface. So surfaces here are the S1 region and S2 region, and the volume fields in the volumes are the psi and phi. So Kirchhoff's method is called as a scalar diffraction theory. That means that components of the scalar function could be x component, y component, or z component of the electric fields and the magnetic fields. So let us find a solution of the waves, diffracted fields, using this Green's theorem. So let us call that the psi is the solution of the wave equation, and instead of phi, let us call the phi as the solution of the non-homogeneous wave equation. Let's say you have a point-like delta function, and the solution is the Green's function, which depends on x and x prime. So call that the Green's function is phi, and solution of the wave equations is psi. So if you insert this to there, what you are going to obtain? So if you insert the information of the wave equations to the Green's theorem, you will obtain the following. For the first term, you have what? Phi is replaced by the Green's function, and Laplacian of psi will be minus k squared times the phi psi. So that will be the following. Green's function, that is the first term. Instead of Laplacian of psi, you can write minus k squared times psi. That is coming from the wave equation. So minus chi squared psi minus the other term psi open parenthesis, and instead of Laplacian of Green's function, you can write the minus k square Green's function and delta function. So that will be minus k square Green's function minus delta function x minus x prime integrated through the volume, and right hand side is the same. A surface integral, Green's function del phi over del n prime minus psi del Green's function over del n prime integrated through the surface. So if you look at the left hand side, we have minus k square Green's function times psi and minus plus Green's function k square psi. That will be cancelled. This term will be cancelled, and then you will left over minus psi times minus plus delta function x minus x prime integrated d cube x prime. If you integrate this phi x prime multiplied by delta function, you will obtain that the phi of x, which is equal to surface integral Green's function del phi over del n prime phi del g over del n prime integrated through the surface. So basically, this is the tool we are going to play. So we know that the Green's function, from the solution of this, we studied that and use time to time. The Green's function is gx x prime e to the I k x minus x prime over x minus x prime. So x minus x prime magnitude is equal to r also. So you saw this in the first part of the course. You can write this solution. So let me write the Kirchhoff's integral, and he uses to explain this to the diffraction pattern obtained by the Fresnel. So basically this is equivalent to the following. So instead of del phi over del n prime, you can write minus n dot gradient of the psi, and instead of this you can write that the minus n prime dot gradient of the Green's function with respect to x prime. So you can write this in that format, and you can take the gradient of the Green's function and plug it there, and you can write this as a following form, and that following form is the Kirchhoff integral. So I will just write the result because we are not going to use. So result, it will be the following. Through the surfaces, that is important, which surfaces are we are going to discuss, that is important. Through the surfaces, we have I think we have a 4 pi here. We have minus 1 over 4 pi e to the I k r over r n prime dot gradient of psi ik 1 plus 1 over 4 pi r at psi integrated through the surface. So you can derive this very easily. All you have to do, take the gradient of the Green's function. If you take the gradient of the Green's function, you will obtain. So we are not going to use this form, but I am just showing you that what is the general form. So if you take the gradient of the Green's function, you will obtain the following: minus ik over r 1 plus I over kr e to the ikr r hat. So basically the bottom line is the following: you have sources, apertures at screen 1 and diffracted fields at screen 2. So you have some electromagnetic waves and some boundary conditions. So Green's theorem tells you a relation between the volume integral and the surface integral. And if you apply this Green's theorem for a wave equation, let's say that the Laplacian plus k square phi is equal to 0, Laplacian plus k square if it is non-homogeneous, if the source is delta function, the solution is the Green's function. So if you use that the Green's theorem with the wave equation, you have the following format. And you can write the del phi over del n prime. This is nothing but n prime dot gradient of phi. N prime is the vector in the inward direction at the surface. And this is the other term, del g over del n prime is n prime dot gradient of the Green's function. If you take the gradient of the Green's function and if you plug it there, you will obtain some form of integral. That form is called the Kirchhoff integral. So we are not going to touch this, but what I am going to do, this have to be integrated through the S1 plus S2 surfaces. This point is important. S1 is the inner surface, that is the place we have apertures, opaque matter or whatever obstacles, okay, which causes the diffraction. And S2 region is the region we observed at the diffraction. If you take the surface integral, you can automatically see that x is nothing but x minus x prime. X prime is related with the surface. If you go to the lower surface S1 and the outer surface is S2, one surface will be unimportant in the integration. Which surface? Which surface will be unimportant to the integration? You have two surfaces, S1, it is the apertures or whatever there. S2 is the diffraction region. Which surface is unimportant if you integrate? So r is nothing but x minus x prime. You are going to take the integral through the surface, the a prime. And so x prime is the region at the dE prime. So if x prime is the region S2, as you see that this is much greater than the region of S1, so the integration through the S2 will be unimportant. So important part of the integration will be the integration from the S1. And integration through the S1 means that the integration through the apertures, okay? So at this point, I can summarize the situation. So if you are going to apply, if you are going to find that the some psi that could be the components of the electric field or magnetic field, you have to take the integration through the S1. S1 region is the region of the apertures. Okay, that's okay. Now let us move on to the Kirchhoff approximation and application of this to the practical problem. So Kirchhoff approximations are the following. So Kirchhoff's approximations. One, what you needed here, psi or derivative of the psi, where at S1. Okay, S1 is the region you have the apertures. So says that psi and del psi over n have to be vanish everywhere on S1 except, this is important, except in the openings. So that tells you that if you have a screen S1, if there are openings here, all information of phi or del phi over L should be passes from these openings, but they are all zero other places. Okay, so if you think about we are going to do an infinite plane with a circular hole, that means that phi and del phi over del n should be non-zero at this opening, but that will be zero all other places. Okay, and the second rule, phi and del phi over del n at the surface of the S1 should be the same as before coming to the opening. So if you don't have any obstacle or opening, if you know that the phi over del n, the value at the opening should be the same. Nothing have to be changed. So basically that means that if the electromagnetic wave is coming to the opening, if the value is E1, Ex, Ey, Ez, whatever, they should be the same at this region S1. Nothing have to be changed. Okay, they should come and pass through the opening. Now, so the approximations are simple. So everything should be zero everywhere except to the opening, and at the opening the value should be the same as the waves enters before the region. Now we have to apply to this a practical case. So now let us raise the Kirchhoff integrals. Some difficulties. The difficulty is the following: if we have some region such that phi and del phi over del n is equal to 0 in both cases, then the solution should be 0 all the places, because if you think about the wave equation such that phi and del phi over del n is 0, that means that the solution should be 0 elsewhere. So Kirchhoff equations, some difficulties, and people inclined to use a more easy format instead of Kirchhoff integral. So the easy format is the following. You know that the two types of boundary conditions. What are those things? You can pick up the Green's function or 0 or the derivative of the Green's function of 0. They are Newman-Dirichlet boundary conditions. You can apply this very easily. So one boundary condition tells you that the Green's function have to be 0 at the surface. Surface means that the S1, and then you have the solution in the following form: phi of x prime del g over del n prime x prime integrated through the surface. So if the Green's function at the surface S1 is 0, then you need to calculate the derivative of the Green's function and find the solution there. And so I think this is a minus sign. So this is called as a Dirichlet boundary condition. And the other condition, the partial derivative of the Green's function with respect to the surface is 0 at S1, and then the solution of the elements of the fields should be the del phi over del n prime of x prime gn integrated through the surface. And this is called a Newman boundary condition. Newman boundary condition. So can we find the same structure? Can we find the same structure satisfying the Dirichlet or Newman boundary conditions for a diffraction? So the practical example could be the following. Think about that the diffraction from a infinite plane with a circular hole or aperture. So we are going to start at a practical diffraction. So suppose that you have an infinite plane, a circular hole. Okay? So the plane is infinite, the electromagnetic waves will pass through that hole and that will diffract. So can we find a Dirichlet or Newman-like boundary conditions for such a diffraction? So maybe we can find. So let us approach the problem finding boundary conditions, satisfying one of these boundary conditions. So Green's function is at the form of what? The Green's function 1 over 4 pi e to the I k r over r. Now think about first an infinite plane without any hole, infinite plane. Okay, suppose that this is a very good conductor with conductivity sigma. If the electromagnetic wave interacts with the surface, what will happen? It will reflect. But at the same time, what will happen? The oscillating components of the electric field will induce a surface current. And that surface current will induce a oscillating in the surface current. So if you look at the two sides of the conductor, if there is an oscillation in one side, there should be an oscillation in the other side. Okay? Therefore, the other side will be all radiating fields. Even the surface is completely closed. If you send the electromagnetic waves, the electric field component will induce current, oscillating currents. Therefore, the other part of the surface will oscillate with the same frequency, and you will have some fields, radiating fields. So, how you can express the radiating fields in the other sides? If there is a source of the current, basically the source of the current is N cross B or H. Okay? From the boundary conditions, N cross B is related with what? Surface currents. So N is a vector perpendicular to surface, and if you multiply this by Green's function and integrate through the whole surface, what you are going to obtain? What you are going to obtain? What is the left-hand side? What do you think the left-hand side? The left-hand side is proportional to the what? So remember that the definition of the vector potential. What is the vector potential? Mu 0 over 4 pi current density times what? Green's function itself. So integrated through the volume. If you remember that the Lorentz conditions. What is the Green's function? E to the kx minus x prime divided by x minus x prime. So basically, you can call that this as a vector potential. You can call this as a vector potential of the oscillating current density of the, let's say, perfect conductor. So is this satisfying any kind of the bounded condition? Let us try. Let us try. So our aim so far is the following. Suppose that you have a plane, perfect conductor, and incident electromagnetic wave. Incident electromagnetic waves induce some currents one side, therefore induce a current in the other side. And that current is related with the N cross B at the surface, because N cross B from the boundary condition is what? And tangential components of the H, differences of the tangential components of the H is the current density. Remember that. N cross H out and H in is equal to surface current density. Therefore, N cross H is related with the surface current density, and the convolution with the Green's function and integration of that should be related with the vector potential. So let us take this, the vector potential in that format, and let us check that whether our results are consistent with the Dirichlet or boundary conditions. So when we do this, you will understand what we are doing. So let us do this. And let us call that this is the z-axis, and the other axes are x and y. And B is nothing but curl of E, and that is equal to I j k del over del x del over del y del over del z. And what else? A. How many components of the A is surviving here? Look at here. How many options you have? EX, EY, and EZ. So, EX, EY, EZ is 0 because the vector potential is parallel to the current density. That's the reason. So you have only EX, EY, and this is 0. So if you take this, you are going to obtain the following. So if you evaluate this, you will get del over del z EYI, del over del z EXJ, some stuff related with the k hat, del over del x EY minus del over del y EX along to k hat. So k hat is not important. So let us look at that the I. So we have minus del over del z EY. This is correct. If you close this one, you have minus minus plus, and you have that one, and you have the k hat. So what is the direction of n hat? N hat is the k hat. So if you take the cross product with the n hat, what you are going to obtain? What is the, this is B, what will be the n cross B? What is the n cross B? So n is the k hat, z direction. So this term will be 0, and that will be k cross I. This should be the k cross j. So what are those things? So what is k cross I? K cross I is j, and you will obtain basically del minus del over del z EY I EYJ, and how about the other one? That should be what? Minus del over del z EX what? EXI EXI. So let me write this again somewhere here. What I find, so k cross k is 0, and I find the following. Vector potential EXI EYJ is equal to minus del over del z EX e to the IKR over R integrated through the surface along I, and other term minus del over del z EY e to the IKR over R dA prime J. So if you look at the component wise, you have one equation here and the other equation here. Now look at the Dirichlet or Newman boundary conditions. So before going to do this, this integral should be evaluated to where? Through the surface. Yes. Okay. Now look at the Dirichlet and Neumann boundary condition, and looking at that, could you say something about that? Are we satisfying the one of the boundary conditions? Are we satisfying the one of the boundary conditions? Which one? Neumann. So psi here could be Ex. It's scalar, x components. And del over del n prime, what is the surface? Vector perpendicular to surface z. So that is del over del z. And the value of what? Ex. Multiplied with Green's function, and this is the Green's function. So basically, this condition, choice of this, is satisfying the one particular boundary condition, that is Neumann boundary condition, and that is also physical, because we said that we have a infinitely long conducting plate, and we said that incident electromagnetic waves induce some currents, and the same currents will be induced to the other side of the plate, and the value of the induced current is related with the n cross b or n cross h, that is better, and the vector potential due to the that current density is nothing but that is the radiating fields. We studied that, and we write this for specific geometry. We know that the Ez equal to 0, and if we look at that the n cross b and plug it there, we find a relation for the vector potential, let's say Ex, which is nothing but del over del z Ex times Green's function over r dE prime. This is the Green's function. You can call this, for this example, the Green's function for the Neumann case. And you can write the same thing for the Ey component. E to the ikr over r dE prime. Now, this is consistent with the Neumann boundary condition. With Neumann boundary conditions. Now let us do the application. So go a little bit forward, and then we will make a study scattering diffraction from a circular hole. Actually, we start the problem as a scalar diffraction theory, but now we end up with the vectorial diffraction theory. So this part is called as a vectorial diffraction theory. So you can make a vectorial diffraction theory using the Dirichlet or Neumann boundary conditions, and we build up a vectorial diffraction theory for a flat screen using the Neumann boundary condition. So basically, if you know that the vector potential, you can calculate that the magnetic field by taking the curl of this, and that will be equal to curl of n cross b e to the ikr over r d prime. Now let us make a small or circular hole in the flat screen. Let us make a flat circular hole. So this was our original screen. It was closed. Now make a circular hole. If you make a circular hole, you have to satisfy the boundary conditions. What are the boundary conditions? I erase there, Kirchhoff boundary conditions. Everything should be vanish at the surface. But n cross b is not vanishing. N cross b is what? Tangent to the surface. Okay, n cross b does not vanish. So what we can do? N is perpendicular to the surface. So the trick is the following. Look at the Maxwell's equations in the free medium. This is very nice. You will see that the very nice symmetry. Curl of E is equal to ik z0 h. Divergence of E is equal to 0. Curl of h ik E over z0 with minus, and divergence of h is equal to 0. So these are the Maxwell's equations. For free medium. So what is the symmetry between the fields here? What happens if I write instead of E as H and instead of H as a E? The structure will be the same, okay? So only you have to play with the impedances and the minus signs, but the structure will be the same. So basically, if you replace the E as a H, this will be H, this should be E, and in order to get this result, you should divide this, multiply by minus Z0 square, and replacing E and H doesn't affect it here, and replacing this by H as E, that makes this one, E as H, that makes this one, so multiply with impedance square with minus sign, you will obtain the other Maxwell's equations. So there's a nice symmetry between the Maxwell's equations for the source-free regions. So that means that you are allowed to replace the field as in the following form. Curl of n cross E, e to the ikr over r d prime. So this replacement is important because this is satisfying the Kirchhoff rules. What is the Kirchhoff rules? Everything should be vanish at the surface. Can this vanish at the surface? Yes, because n cross E is a tangential electric field to the surface. So from the boundary conditions for the perfect conductor, tangential component of the electric field have to be vanished. Okay? And if you take this integral through the surface, through the whole surface, at which points you will get a non-zero integration. All the surface, n cross H, is a tangent component of the electric field, parallel component of the electric field, which is equal to 0. So n cross E in or E out, we said that have to be 0. So basically, the tangential component of n cross E have to be 0. All conducting surfaces, only part could pass from this hole. Okay? So for a flat surface, we are satisfying the one type of the boundary condition, Newman boundary condition, and we are satisfying the all Kirchhoff rules. Why? What the Kirchhoff rules are saying that this or that should be 0 except openings. So all stuff here 0, all n cross e stuff is 0 on the surface, only passing things from the hole. So basically, taking the integral, let us call this aperture. So let us call that this is the circular aperture. So this integral will be non-zero. If you take the integral, that will be non-zero through the aperture, that is n cross e, e to the ikr over the e prime, and that field is called as a diffracted field. You will do the same exercise with that for the magnetic field, but in that case you have an integral from all over the places. So if you choose that this one be as a in that form, you have the integral from the surface and from the aperture. But if you pass to the electric field and you have n cross E tangent component of the electric field, only surviving part is the aperture. All everywhere is the electric field is 0. So this is a very nice and tricky stuff. So we started to find something consistent with the boundary condition Newman, and that brings that give us that the magnetic field, but we are not happy with the magnetic field. What we do, we look at the Maxwell's equations, we change the fields, because in the Maxwell's equations there are very nice symmetry between the Faraday's law and the Ampere's law for the source-free Maxwell's equations. We write the electric fields and then we take the whole integral for whole surfaces, and we said that that integral is surviving only through the apertures. So next thing, I will study that the diffraction from the circular hole, practical application I am going to do. So I summarized the all diffraction theory very quickly and very oversimplified way. If you look at your book, it is rather complicated form. So I combine everything in a 1 hour. So I make a summary for the scalar diffraction theory and vectorial diffraction theory, and I find the boundary condition satisfying the Newman boundary condition, and I find the form of the diffracted electric field if you have a circular aperture in the flat screen. So 10 minutes later I will do application.